I think I slowly recall to you what we went through last time. Then tell some what when I first learned it, remarkable facts about these local algebras and thermistics. So last time what we did was to look at the Riddler wedge. So the Riddler wedge has two halves. So there is the wedge is space-time is lying in the 1-0 plane, and the W, which I denote by W, is the right wedge, and W prime is the left wedge. And one knows that these two, any 2 points here and here, are space-like right wedges. That we know. And geometrically, the Lorentz transformations in the 0-1 plane, which is just this matrix here, just what I think it is called high energy scattering as a boost or something. I don't know, but it's a phrase for it. So it's just the Lorentz transformation in the 0-1 plane doesn't do anything to one another. You have 2 and 3. That is, and it is the lambda W, and I'm calling it lambda WT because it definitely is a right wedge invariant, but actually it also is the left wedge invariant. So this Lorentz transformation is both the wedges invariant and creates orbits which are corresponding to constantly accelerating particles, as is well known. So the lambda W acts here and also there. And there is also another operator, which is the operator called JW, which flips the sign for the naught and the 1 axis. So geometrically again, it corresponds to, in space-time language, corresponds to a CPT transformation, which removes all the signs, followed by a pi rotation around the 1 axis. So if you rotate by pi around the 1 axis, it will reverse the sign of 2 and 3. So it will be this JW I have written down.
You have a space like it is software space like.
Yes.
And we learned that cannot connect space like regions without violating the
I will.
AW that is going to map or connect.
There is no signal going from W to W prime.
But what is the role of JW then? Go from one ring to other ring.
It is just an operator. It's in the Lorentz group, concrete group, and we use it, for example, when we discuss CPT theorem. CPT theorem also does the same thing. CPT operator geometrically also does that. Takes future to past, right? CPT. Okay? But you can't make a transformation from actually from future to past. So it's just a transformation which seems to control the interactions of quantum fields, and indirectly it has consequences. So I will.
Sorry, Bal, your slides are not changed. I'm not able to see the slides change.
Oh, is that Babar?
No, this is Bala.
Bala. Which is complaint is they can't see the slides change. Can somebody help? The sharing has to be done. Do you know? Huh? Do you know how to make sure that Bala sees it?
Click the green one. I'm not sure. Say,
We are trying our best.
Okay.
Which one does he see?
You can see how to quantize local while algebras, addendum to Thursday 23.
So this small JW is a geometrical thing. Okay? I'm not giving this interpretation in terms of it will play a big role in causality, and I'll show you why. You see that the local fields we construct in right and the left edge will actually commute. Okay? So this will be the independence in quantum theory of experiments done in W prime being statistically independent. So we will get that answer out. Okay? We did it last time. Okay? So, so what happens? I remind you what happens then when we go into quantum theory. So this JW and the Lorentz transformations commute because Lorentz transformations is in the 0, 1 plane, whereas small jw is minus identity in that space, so they commute. So if we look at the operators which represent them, which I call rho, the representation is called rho, then this equation says that rho of lambda w is, can be written as exponential of ITKW, with ITKW is the KW is the boost operator, and this is the generator of the boost transformations. Whereas the representation of this small jw is another operator, theta, which we call capital JW, which is the CPT operator multiplied by a pi rotation around the one axis. Capital JW is anti-unitary, whereas the rho or lambda w is unitary. And geometry, because of this relation here, is to commute. So we want to see the consequences of this computation. Well, if you don't see it, just tell me. We saw that the important consequences, because of the I there, what happens is you want the capital JW anti-unitary to commute with exponential ITKW, and because of the I there, the capital JW must anti-commute with KW, not commute, but anti-commute with KW, because of the I. This is quite similar to the analysis of Wigner to maintain positive energy in the presence of CPT. So he proves that if the energy is positive, CPT must be an anti-unitary operator by an argument quite similar to this. It's not a choice. If you don't have it, the Hamiltonian will not be bounded. Okay. So JW anti-commute to KW. So exponential minus PKW, what it which we call delta W to the power half, and reverses the sign when you conjugate with J. So we put K, because K reverses the sign. So this reverses goes to its inverse. Okay. So what we did last time was use this capital W and square root of delta W to construct what we call the modular operator, which I call SRW. And the SRW has the important property that it is because J anti-commute with delta, to pull J through, okay, because delta is a minus half of times J. So the square of S is 1, like the square of J is 1. The square of S is 1 because the two middle things, this delta to the power minus half, this will cancel. You get J squared is 1. And so S squared is 1, and likewise J squared is 1. J squared is simply pi rotation followed by CPT, and for integral speed of fields, both square to 1 separately. So J squared is 1. And yeah, so that's what we had. And then we used this S, which is anti-linear, to define what we call as a real subspace. So my rest of my talk is to tell you what is in the Hilbert space of the one particle representation of the spin massive integral spin particle I am looking at. Okay. So I want to pick what is called as a real subspace. The vectors of the real subspace of the topic, and then a Hilbert space will change. We will see in a minute that this is exactly equivalent to my original choice that the test functions we use to smear the field are real. Okay. This equation here reflects the fact that when I smear the field with test functions to construct the Weil algebra, I have to use real test functions. That equation is this one. They are related. I'll show you how to get this. That I think is a very interesting fact. And from there you will be dictate what. The S operator on the left edge is obtained by conjugating the S operator for the right edge by the JW, because JW takes right edge to left edge. So we can look at this operator. We are conjugating SW to JW, but S has a J on the left, so that cancels out. And you get delta to the power half times J, which is J times delta to the power minus. So it is changed. This S or W prime is not the same as S or W. It is different. So the what we call real surface is different. It's a thinking of vectors of the input place, and they are different at the left and the right edge. Okay. Given this class, last time I proved causality. First, I proved that the beginner symbol W came. I proved that this is. So we wanted to prove that they commute, where this eta from the left and the right edges are real vectors. So they gave you the Weyl algebra. So this equation is proved. I'm going to show that they commute, which was the same as showing that the product of these two things is given by this equation, where on top what you get is the imaginary part of the scalar product of the two vectors, and we have to prove that this scalar product is real. If it is real, the imaginary part is zero, then when I flip W with W prime, this doesn't change. So they will commute. So this is the crux of the argument. How does it happen that this is real? Okay. That I did last time, but no harm in repeating. So I took this eta W prime with theta W, but eta W prime is a real vector. So S of W prime on eta W prime is theta W prime. Likewise, S of W psi W is psi W. So I put S in front of this with two different S, because they are corresponding to different real surfaces. Then write down the equation by J on the left edge and on the right edge, and use the fact that the J is anti-uniform. So JW and JW prime we get, but the J's are not changed because they are conjugating delta with J. So this is J. So this J and this J are the same. So because it is anti-unitary, I can rewrite this as this right hand side as the order of the lattice. So delta to the power of half side goes into the bra vector, and this one goes to the cake vector, the two J's cancel. But these are simple operated. So I can pull it out and cancel this. So this is equal to left hand side equal to psi W times eta W prime. It shows which is the complex conjugate of this equation, this scalar product. So we have proved that this thing is real.
So can I ask something, Bal? Can I ask something?
Yeah.
So how come we have real vectors here? How come, like, why are we focusing on this subspace which has only this real scalar product?
No, scalar product is not real. Scalar product in Hilbert case is complex. We are working with a complex Hilbert case, but in the definition of the Weyl algebra, the top what comes in the Weyl algebra definition is over here. This here, by definition, is imaginary part of the scalar product. By definition. Right?
Yeah, that's fine.
Right?
Yeah, that's fine. But then you showed over here, like in 5 point, then your whole argument was that if you consider these vectors, which are, I suppose, are projections using this S, then these have no imaginary part in the scalar products across the two. Oh, so that's what you're proving. Okay, I got it.
They are the real scalar product.
Okay, fine. I think I got it.
That's what you're asking. But this is not scanning the full Hilbert space. The full Hilbert space is the real part of the Hilbert space, and the rest plus I times the real part. So by definition, the full Hilbert space is the direct sum of the real part of the Hilbert space divided by 1W, and plus I times the same real Hilbert space, I times the you take the direct sum. Then you take it in the manifold, that is a full Hilbert space. technically you have to close it, but never mind. Okay, so this is not a full Hilbert space. For the fixed vectors under W, they happen to be real. And you see what that happens in another, perhaps clearer way in a minute.
Okay.
Okay, so yeah, you see why this happens. I have written down that this causal complement that I am writing here is often called as the symplectic complement by people writing this field, because the antisymmetric form that comes between functions coming from the causal propagator happens to be antisymmetric, and if you take out from kernel, it's in fact defining a symplectic form. But anyway, that's all for just a language.
Sorry, SW and SW prime both define some real space, but they're different.
Yes, real subspace.
But
Of
they're different.
the right
Oh.
for the right wedge.
Okay.
So it's not, does it mean that any vector in the Hilbert space has you cannot define a reality for individual vectors of a Hilbert space. That doesn't mean, because the Hilbert space is an abstract object. However, I can, because Hilbert space is a module over complex numbers, you can take linear combinations with complex coefficients. The real subspace means that I'm only taking linear combinations with real coefficients. That's all I mean. Okay. So it is not reality in the sense of some function on somewhere being real. That is not what is meant. The real vector space doesn't mean that the vectors or the underlying space are real. That doesn't mean that. It means that the coefficients are real. Okay. So that is also significant. And in this short.
No, but I still have a confusion. Maybe I didn't follow the whole algebra. So you showed that the while operator commutes, but only for the real subspace. So, but shouldn't we expect it to commute for all the vectors on the right wedge and the left wedge?
No, it will not. It will not commute for all the vectors of the Hilbert space, for sure. Because you can see that the causality is even for massive scalar fields in ordinary field theory. If you take the field, well, phi of x and phi of y will commute except by a space-like separated. But suppose a smear phi of x with some test function in say w, which I will do in a minute, and another test function, call it f, so w of f, and in y I'll smear it with test function called g to get phi of x, phi of f, phi of g, and again take the commutator. You'll find that the zero will only if f and g are real. In the normal sense of decimal, normal sense of function. Okay. You see that if you put complex functions there, it will not vanish. In fact, you end up by taking some scalar product of the function. So the scalar, it is you unfortunately know it. People like Abhay have written that the scalar product of two vectors in a Hilbert space, the real part defines a norm and the imaginary part defines a separately form. So they have used this concept in some other work in quantization of quantum gravity type arguments. So you see that quite explicitly. So if you smear with complex functions, any quantum field is a complex function. It will not complete commute. So when the two functions you smear with are not even if they are space-like supported, it will not commute. So you can say it another way that they are not Greenwich complete. To smear a Greenwich scalar field with a complex function will not be a self-adjoint operator. So that may be another way of seeing why things go wrong. Okay. So this is a small blurb to say that because of the fact that the Tomita-Takesaki operator is unique, there's one, once you fix the algebra in the cyclic vector is a vacuum, and the algebra is the algebra on a wedge, then S is fixed. There are no two S's. Okay? So if you find some other F by some other S by some other means, by general theory, you know that you won't get anything new. Okay? So let us keep that in mind. So that is the part there. And I want to tell you what is the meaning of a real subspace of S localized in some region coming from the algebra, while algebra in some region O, like a while, like the base. I think this is a quite interesting analysis in Fourier transforms. By the way, I should mention that Fourier transforms, well, it has been known that they play a very important role. Okay? But recently, there have appeared quite deep papers. Well, let's say review type papers of quite deep results on what they call tubular localization. That is, what is it called? Yeah. If a particle is going along a time-like line, and you make a tubular region of that line, it is slightly make it fat. And look at the algebra observables in that near that tube. There are a bunch of results which I did not know due to Borges, proving that this algebra, if you measure all of it, that guy who is traveling on the line, if you measure all this stuff, he can tell completely what happens to that algebra to all regions which are causally connected to it. So it will get very fat and fill the whole region. Okay? So it will, for example, in the Rindler case, if you have this accelerated particles on this line, if you thicken that, so let us assume that the person is rather fat. So he goes around this line, constant acceleration, and measures everything that can be accessed. He will know the entire quantum theory or the Rindler waves, okay? Just by that observation. This is Borges' result. It is the result is very surprising, okay? And to prove this result, one pulls some rather technical results, actually physically interesting results from Fourier transforms and what is called the theory of wave fronts. So in this paper by Edwin and Promeyer, they have tried to give a pedagogical review of this whole stuff. It's certainly worth reading, but I would not say that it is easy reading. It's certainly full of physical ideas. Forget the maths. The physical ideas are very beautiful, very powerful. Okay? So one should know what they are seeing. Okay? Some other proofs, but they are not given there. Okay? Some of the proofs are, but they are referred to appendices or they give reference to other papers. If you accept it, it is what they say is already very, very striking, and it can be, I am sure, can be used elsewhere. So one should pay attention to this kind of Fourier transforms. One should pay attention. So when you bring Fourier transforms, I want to see what will happen. There is an analog of the kind of result I am going to tell you with Fourier transforms. Okay? So imagine a function which is say I am taking a function f with the it's the it will be the Fourier transform of another function we have taken it, which is localized from 0 to 1 half line. So the f tilde is localized on a half line from 0 to infinity. Let us see, and look at the Fourier transform. The Fourier transform, you can see from here that if I take omega, the transform is defined for real omega, but if I make omega a complex variable and try to put imaginary omega here, you see that I times imaginary part of omega will give exponentially damping factor. So you find that when you go to the upper half plane, this object here under some smoothness condition or a tilde, it will actually become a holomorphic function. So you will find that the f of omega I am looking at on the left hand side, the boundary value of a holomorphic function in the upper half plane. Okay? The boundary value may be complicated, maybe some distribution, whatever. You could have kings and so on, but it is a boundary value of a holomorphic function in the upper half. Okay? So this is a I think Very interesting result. Another thing is, because I have written omega and x, you think of x as a frequency of speech. And if you imagine that human speech is bounded, here, suppose you assume, as is done when telephone analysis is done by telephone companies, our frequency spectrum is bounded. Suppose you do that. Then omega, the right hand side will be our time. Okay. So change the notation a little bit and imagining that x is the frequency of our speech and omega is time. Then till that the frequency spectrum is bounded, the Fourier transform in time is a have holomorphic function all over t. What does it mean? That will mean that if I know what the speech is like in an infinitesimal amount of time, because of holomorphism, I know it from all time. So if somebody he asks me a question infinitesimally short in time, I can tell you what he will tell me ever. In the past, the future, forever. It's an astonishing result. But nevertheless, people use this analysis routinely when you people analyze telephones, for example. They assume that the frequency is cut off in the telephone speech, and they're able to manage it. Where does it go wrong? I suppose the neglected parts in their calculation is irrelevant for them. But it is an amusing anecdote on an amusing example of the power of Fourier transforms. Now, what do I want to do? I want to apply this result to the Riddler wedge. So I am going to take the right Riddler wedge and imagine that the momentum space functions I'm looking at, momentum space functions, the momentum t, are Fourier transforms of some function is supported on the Riddler wedge. So x plus and x minus are divided by x plus minus x 0. And for the right Riddler wedge, both of these are positive. Okay. So x plus and x minus are positive because of the fact that I am in the right Riddler wedge. So when I take the Fourier transform, here I will integrate from 0 to infinity of both x plus and x minus. I am neglecting here 2 and 3 coordinates because they play no role in this calculation. So I just do the analysis in the 0, 1 field and I take the Fourier transform. What will I show? I will show you that the requirement that SW is the left hand side, the analog of my H in the inverse space, is real. The sense that S is alpha invariant means that this alpha tilde is coming here is actually a real function. That is, I will show you that this alpha tilde integration between being real is the same as the left hand side of P being real by the Tomita of it. Okay. So I'll show that. It is quite surprising. In bonus we will start getting this KMS text results automatically from here. So we'll see what happens. But this requires the positivity of energy. So otherwise the results are wrong. So what do I do? We know that only for positive energy representations, the P0 is larger than P1. So this P0 is larger than P1. So I will rewrite this equation in terms of P0 minus P1 and P0 plus P1. They're both positive. And I'll try to see what happens. So I just took that expression and substitute P plus minus, which is P0 plus minus P1. But because of the positivity of energy, P0 is larger than equal to P1. So P plus minus are positive. That is important. And I'm integrating over x plus and x minus in the Riddler wedge. Okay. So I got this thing here. I want to apply to this expression my SW. You see what happens if the left hand side is real in the sense of SW. So under boost transformation, what happens is that we know that x plus will undergo a boost scaling. I think all of you know by some exponential t, and x minus will undergo a scaling with exponential minus t, and you get a minus sign. Okay, because of the you can see that we put this. Whereas this is cos t plus I shift t. The other one is maybe the other way around, shift t minus cos t. So you get minus sign, you get this exactly this expression, and this obtained by applying this expression ITKW here. So I'm making a boost of this expression in Fourier transform I written down using standard calculation. It's nothing fancy. But p plus and p minus are real. Now I take this expression and ask myself, what happens if I make t a complex variable and let so I let t as the expression I knew and let mu go from 0 to pi. Okay, what happens? I think this is the surprising fact. So you just take this t and for t you write exponential I mu and write exponential e to the power of exponential I mu as cos and sine factors, separate it out, and you find two terms. The first term has a cos mu, I times cos mu in front of p plus x plus minus p minus x minus. The second one is more, it is deserving more our attention as a minus sin mu times p. First one is an oscillatory factor, which will not tell you anything about convergence. It is an oscillatory factor, you can easily see by taking a modulus that it is relevant. The second one is more dangerous. P plus and p minus p plus x plus is positive. So is p minus x minus. So this expression here is strictly positive in the region of integration, and you have a minus sin mu. Okay. So this term is well defined only in the region where mu lies between 0 and pi. Okay. If mu lies between 0 and pi, the sin mu is positive. So this is a damping factor, and you're okay. Okay. So this is definitely converged. So we can, and from technical assumption, you end up by proving that the left hand side can be analytically continued in the t plane in the complex direction up to from 0 to pi. You can thicken the real axis in t, you can thicken to pi. Okay. You may notice that this is quite analogous to what happens in the KMS. So I'm making t complex, imaginary, or if you like exponential minus beta t, that capital T that comes there, I'm making complex and going in the complex, the imaginary direction, but I can go up to pi. Okay. So I can make mu go from 0 to pi. Until then, this is well defined. So in this region, it is a polymorphic function. So there is a whole strip in the t plane. Till real doesn't make any difference. There is a whole strip in the t plane of thickness pi, where this expression is a polymorphic function. And I want to see what happens. So, yeah. So I want to see what happens. You know, if I take imaginary part of t, go to the boundary. Okay. So the boundary of this thickened region will be pi. So then we take the boundary pi, and then you find that this expression here, sin mu goes away here, and cos mu becomes just a minus sign. And you get this alpha t then here, cos this becomes minus 1, you get this expression. So this is the effect of the modular operator. Actually, the modular operator, you will notice that this is minus 5 kW plus square root of my delta W. So square root delta W acting on this alpha W is this expression. Okay. So now let me apply J. J is anti-linear. So I apply S. These are all real, but this alpha tilde W becomes complex conjugated, and this I makes this back to plus. So applying SW on this on the Fourier transform says that this alpha W in the original Fourier transform is mainly complex conjugation. Okay. So if you want a real surface, you have to choose this alpha tilde to be real. So the reality coming from Tomita Takisaki is the same reality or the test functions. This alpha delta W is a test function we use to smear quantum fields, and the reality of the test functions I used earlier is the same reality that comes here from physics. So they are actually coinciding. Okay? This is a very helpful result for further developers. So it may let you think about this whole problem in language which is familiar to you, maybe.
You,
Hmm.
when you pick mu to be 5,
Hmm.
then you want to have mind that we are made a T from I knew difference is x1 minus x0 by T.
I don't change anything. I don't change x0, x plus and x minus. I only t is the parameter which comes in front of p plus x plus p minus x minus, right? So I don't do anything to x. Huh?
Just the Fourier definition.
It's just a Fourier, two-dimensional Fourier transform. Okay? But I'm just making the coefficient of the Fourier transform and trying to see how far I can go with t in the complex direction. That is all I'm. By the way, this kind of analysis, this people trying to analyze singularity structure of quantum fields in gravity or even in cosmic space use something they call wavefront analysis. Wavefront analysis consists again of such Fourier transforms, but it is shown that the singularities are along certain lines which are related to light propagation coming from the operator. It is proved by Ratzikowski and so on. Okay? And it is quite, the singularity structure is coming from light cones. They prove. And this Stromeyer written paper again reproduces that proof in a simple way. So these are all related. And for good or for bad, we cannot avoid some knowledge of Fourier transforms. Not in the trivial way, but in not just going backwards and taking inverse transforms and so on, but at a more sophisticated level, in a way we can apply. So one interesting fact that comes here, I think, is that when you go here, you see that there is an inversion of the kind of inversion you are talking about. P plus and P minus are getting reversed. Okay? From here, before I apply the J operator, it seems to be reversed. Okay? So the modular operator is reversing the momentum. So if at least we can imagine that it is like reversing the momentum in Feynman's diagrammatic. The part of traveling back, particles traveling back in time, being antiparticles, it seems to be related to that. So the delta to the power of half I am applying has a property which seems related to reversing, for example, the scattering process, reversing two of the lines. For example, if I reverse the line 1 and 4, I get this diagram, which is what we would used to call as crossing diagram, a cross process. At one time, we used to call this as a crossing relation. So it looks like this square root of delta is related to crossing relations. It appears, this speculation you can see in the paper of Hassan and Schroer long ago. And apparently, this has actually been proved recently in two-dimensional quantum field theories. I think they proved that 2 plus 1 theories, the boundary lines, gives you a conformal field theory in the boundary, apparently has been proved by Lechner and so on, but I don't know the details. There seems to be literature on this, which one can trace. So it's quite interesting. So in case, what we need is real subspace of the Tomita operator corresponds to real functions used as test function. That's what we want. So I want to sharpen the localization using this type. Now I quote result, which I will not prove. Okay? Namely, you may ask now, first notice that it is a general theorem that any causally complete region, so somewhere I have defined for example, I can produce this wedge, what is it, this causal diamond by intersecting two wedges. So this will be a wedge localized at this point, and that will be the wedge localized at another point. So I translate the tip of one edge to the right, left, then intersect it. You get the causal and intersect it. The points common to it is this causal diamond. So the theorem says is that this is also a good reason to discuss this algebra localized here, which is also good causality problem. In fact, this is a standard thing that we use in discussing causality. So you might ask, what is the real subspace here? Well, for this region, and it turns out that the real subspace or the Hilbert space in the intersection region is the intersection of the two real subspaces of W1 and W2. So there is some nice property that we can intersect the two regions. The Hilbert space, take all vectors in XW1, real part here, intersect, you get some real part there, and that will be invariant under both the modular operators, and that is the one appropriate for this region. Okay. So we can find out what it is. Okay. In fact, and then we can, I must warn you that I find it only in principle. If I try doing it by hand to see what it is, I try to write the Tomita operator. You can write the Tomita. I will also tell you how to find the Tomita operator in principle. But you try to do it by hand. I should say that it is practically, at least I don't know how to do it. And the only person who has attempted this is for conformally invariant theories, where he took the fields in one Rindel wedge and conformally transformed the Rindel wedge to this causal diamond very carefully and found out what these operators are. But he cannot proceed beyond that. So we don't know as of now what is the explicit formula for the real subspaces. But I can find the real subspace.
But Bal, can I ask? So wasn't like this operator related to some kind of continuation of the boost operator?
Of the what operator?
This Tomita operator, wasn't it related to some continuation of the boost operator and then
We
taking?
don't know. I don't know. But what it is simply related is to take test functions which are real in this intersection. To take real functions in this intersection, their Fourier transforms, which will give, but how do I take Fourier transforms in this part? So, because this is a small part, so how do I take Fourier transforms? Because you need to integral all. So there is a technique by multiplying this function supported here by some cutoff function, okay, which is localized here, and then you take Fourier transforms. There is a whole.
No, but about your comment that you can't construct the Tomita operator explicitly. So that's what I was asking. Why not? Because like if you start with some free theory, you know the expression for the boost operators. So you start from there and just follow the formulas which you have written. So it's some kind of a analytic continuation of those operators and some square roots. So why not? Why is it so difficult?
I don't know. The two Ks that come are not continuations of each other. They are boosts corresponding to two different wedges. So how do I match the two boost operators corresponding to two different wedges? This I do not know. I do not know if it can be done. It will be very interesting if it can be done, but I don't know how to do it. And I will very quickly point out something even stranger. Okay. So I have a real subspace here. The real subspace at the Hilbert space level may be difficult, but at another level, maybe not so difficult. If they got functions which are real in this small, in this causal diamond, and smear our standard quantities with this real function and you exponentiate it, you get the Weil algebra there. But there's something strange happening because so I don't know what the boost operator is, and I don't know what is a J, what is a CPT on this base, on this constant diamond. What corresponds to J? Yeah, I don't know. It exists, but what is it? What does it do here? It will transform this diamond to the constant complement. I suppose constant complement we can find. But there's a K that comes associated to this diamond, and this K operator acting on the vacuum is zero. Okay. This K operator, like all these Tomita operators, all the Tomita operators are zero on the vacuum. Otherwise, the construction won't go through, and there's some separate proof that will give you. So you get infinite number of exponential ITK annihilated in the vacuum, unitary operators annihilated in the vacuum. They look like infinite dimensional local symmetries. Each K is associated with some local region, and they are annihilated in the vacuum. So they look like gauge transformations leaving the vacuum fixed. What is it? Do they come? What is the algebra? What kind of gauge group are they generating? What is it? I don't know. What are the physical consequences? I don't know. Which appears to be a very much open problem in this world today. I think it is somewhat astonishing that this should happen. And to understand it would be, even in some trivial model like, I don't know, two-dimensional, one space, one time models. That gives kind of JT gravity, something
But,
like that.
Bal, so you're getting these infinite number by considering different wedges or what? How did you go from?
The real surfaces are going to be different in each of these cases because they depend on the real functions. Functions which are real and supported on this. Say here, supported in this constant diamond. They are different functions on the right edge or the left edge. So they're completely dealing real. There are different real surfaces of the space of all functions, depending on your, say, some scalar, some seem infinity function of R3 or R2. They're quite different. So there are a huge number of real surfaces of a complex function space. So each one will give different answers. There are different implications. So what do we do? For example, Raphael Sofkin Johnson vacuum is modeled on using this constant diamond, and he has developed a formulation. Sofkin Johnson has developed a very nice formulation on how to quantize PCA. It's not the same as what I am doing. So this is a preferred playground for people doing this kind of calculation because the constant diamond is much simpler, especially one smaller one time. The release function is some test function epsilon of x0 plus 1 and minus 1. So you can handle many things quite easily. And Raphael and his collaborators have looked at this and Dow correctly and looked at it. But if you change this as you can, the answers will change. How do they change? They don't know. So there is something going on which seems to have physical implications, which seems to me an open problem. So one should think about it, an open problem. Yeah. This is one of our areas of ignorance. I think we should look at it more carefully. Okay, so let me go on. Then I'll finish up. The result due to these people apparently did not is that this kind of first result that I have figured out that you can get all possible. What is it? Well, I have not written. I have written here, but I have not said today that there is something called causally complete regions. Okay? Causally complete regions physically means that if you take 82 points in that region, A time-like trajectory from one point to the other lies entirely within the region. A time-like or light-like fusion pointing. So it's almost like a space-time, and it will be automatically what they call globally hyperbolic. And the result is, you take some region, call it O, take its causal complement, so all points with a space-like electricity, take one more complement, you take O double prime. O double prime is always causally complete. That is the proof. Okay? So these people deal with only causally complete regions, and in Haas's book, you see a proof of the causality statement I made in minute ago.
But
Why
why would O double prime not be O itself?
It can be O itself. O double prime can be O. For example, causal diamond, which is an O double prime is O. Okay?
No, but
Or any
my question is, how can it not be O? Wouldn't it always be O?
they are. Okay. You are asking for an example where O double prime is bigger than O. Okay? I should say I don't know. Okay? But there must be examples. Well, the kind of picture, the kind of picture, if you look at the paper of Edgerton and Stromae, they have written down causal diamond, and inside that they have written a fish-like region, okay, which they start by discussing as their O. Okay. You take O double prime of that region, it is filling the entire causal diamond. It is no longer what we started from. So that is an excellent example of what can happen. The time-like tube theorem of Schroer is addressing of Barclays is exactly addressing this issue. So if you look in the Stromae picture paper, you see a picture, a figure where you have a causal diamond, and inside that there is a blob. Okay, that blob is the region for two them is the O. Think of that as O. Okay. And you take O double prime, all the commitments, you will get the entire thing. So it can get patterns in non-trivial ways. And as I say, the time-like tube theorem is quite important. Okay. So you take causally complete regions, and it is known, it's a very result in Lorentzian geometry, that which I don't know the proof. Okay. That all causally complete regions can be obtained by intersections of wedges. So suppose you take some causally complete region and take all wedges which contain that region and intersect them. You will get back that causally complete region. So every causally complete region is the intersection of wedges. So this is some results in Lorentzian geometry, which I don't know. So the theorem is the functions supported. So this is an important result. Okay. So let me see what. So what do you see? Now we can ask, what are the functions which are supported here? Okay. So all the regions of interest are coming from trillion regions, so intersections. Okay. This is interesting. And the real functions for as test functions for my fields are coming from functions they are supported in this in this causally complete regions. So I can smear them, and you will see that they fulfill, and they have a Tobita operator because of the test. I am not giving you the proof, but there is a proof that there is a way to take Fourier transforms. And so also the functions are supported in small region. There is a way to define Fourier transforms, and it will again have a Tobita operator at a G. And there will be a boost operator associated to it. What does the boost do here? It will, by theorems, we know that exponential ITK will generate an automorphism of the algebra in this wedge, in this region I am looking at. It will not act on the other one. It's not even defined. You take something else, some other causally complete region. But it has the nice property that they will all these boosts are zero on the vacuum. With respect to which I am taking expectation. All of them are zero. So there is and there, we can think of them as localized in this causally complete regions. So infinite number of operators which are vanishing on the vacuum. That is what I have been taught are symmetries of the vacuum. Are they? What are they? Infinite dimensional symmetry, what is it? What is the algebra they intergenerate? And I see, I don't know the answers. I think that conceptually these are very interesting questions. So, I'll finish up mine by a small calculation that for every one of these local algebras, the quantum state I write down is thermal. So the quantum state I am going to write down is by taking expectation values of two operators. Okay. In the vacuum, the operators are localized in some region or some local region like this. And I take that thing, vacuum expectation value, and I show you that there are KMS states, they are thermal states. What do I mean by thermal states? I remind you of what the meaning of thermal states. Suppose rho is a density matrix, and I take the expectation value of two operators with regard to rho, is a trace of rho with A. Nowadays, with trace of rho. But trace of rho can take it wide. But this you can write, as you know, as B exponential minus beta h, same rho, B exponential minus beta h, A exponential B minus B plus beta h. If you write it down in trace, rho will become exponential minus beta h. By simplicity of this, you cancel the last bracket, and you get back the left hand side. This equation involves this A in imaginary direction with regard to the Hamiltonian. So it involves this A in the direction I beta. So this U of I beta actonic. U of I beta is the time evolution, then imaginary direction in the space getting involved. This temperature, imaginary temperature, or real time getting involved, and you get this equation. Left hand side is equal to right hand side. Now, this is the characteristic of any of our thermal states, but the Hugo-Martin-Schwinger surface, that this result is much more general, and it is necessary if we want to take infinite volume limits of statistical mechanical systems. So, this was announced long ago by these people in a meeting which took place, I don't know, in somewhere in the US. This result was announced. So these are the Hugo-Martin-Schwinger states. So what is relevant there? These are the first question is asking. Now I show you that the vacuum expectation values of any two operator fulfilling the Tomita conditions fulfill this criteria. No matter what. So I will say any state omega rho on on operator algebra is KMS if this condition. So let me look at a case where I have some real subspace localized in subspace and region. So I should have written W here. This is a wide operator. I should have written W here corresponding to W of H, and we have proved already that SW acting on this is W of H star. The star is coming from the exponential, that imaginary part has an I in front, with the wide algebra. So it remains so take WH will become W minus B of H will become B minus H. And, so it fulfills this equation. The algebra generated maybe fulfills this equation. And SW are the vacuum set. The vacuum, the rotation of this equation. So it will be in this way. It's a boost and a CPT operation and then rotation. So you can change this. Okay. Now let me, given this, let me go back and look here. There is some algebraic mistake. Having mistake, it should be 0, not 0, 0. So I take the expectation value immediately between the vacuums. So any local region, I take it. A and B are central operators. So not central. by definition of star, this is A star of P0, P of P0. Okay, by definition. But this A star of the vacuum, by definition, is equal to the Tomita operator A on P0. By definition, because Tomita operator makes star into no star. And likewise, on the right hand side, you get B is equal to B star. Okay. Now, J is anti-unitary. So I can cancel them, but I should divide the bracket. Okay? So it will become square root of delta W B star is 0. Square root of delta W A is 0. But this is second join. So this is first I can take up first I can take up delta W square root and I get a delta W. Okay? Then I take up B star and I get a D and I get this equation. And this A I can put in front. So you can go back here. So first I take out the square root of delta outside and the A. So I have the A here, the square root of delta. Then this square root of delta I pull out, then between this delta. Then I get pull out B star, I get B. So you find this equation. So, but vacuum is delta invariant, so I can conjugate it by this equation. So you find that this is equal to this is equal to this. So delta W is like this expression minus beta. So the delta W was expression minus beta times boost operator. So you find that this is the KMS condition, that what is replacing the terminal temperature is expression minus beta K, where K is the boost operator corresponding to a Riller wedge, but in general we don't know what it is. That is equal to side. So we ended up at 2 here it is. So the terminal state I am writing down corresponding Hamilton is of the normalization given by 2 pi kW over beta. So this is a proof that all local algebras, the vacuum vector and all local algebras is a mixed state. It has an entropy. You can try computing it, you get infinite, but there is relative entropies. And many, it has become an industry, you try to compute the relative entropies or two of these things. So there is a way to do it due to Arachne, and you can do calculations and get an answer. So I think this is a very important result, that there are no pure states on the local algebras at all. Okay? There is no such thing. Anyone who is trying to say vector space or a local algebra, there's at least, or they are either doing something wrong or they are leaving quantum field theory as we know it today. Maybe there is some other quantum field theory where it is okay, but the present quantum field theory you can't do. So with that, I will stop here and this kind of construction you can keep doing. I will make some more remarks on how to pop. So what you have got here, make one remark, is that you have taken Minkowski space and populated it by these Hawkely complete regions, the intersecting and so on. So a whole lot, infinite number covering the whole space time. And it's a directed set. So you can say that some causally complete region is the future of another causally complete region. So there's an arrow. So it's a directed set. Each of them are given an algebra of operators. So what you have got with this Tomita operator. So what you have got is a net. This is what they call a net of this algebras and this Tomita operators. Whole net. And what is causally space-time is only playing the role of here of an indexing set. So the indexing set having some properties, and that's all it is playing here. Question: can I recover standard space-time it is topology and the it's concrete structure from here all over. Can you do it? The answer is not no. It's open. It is not no. I suppose so, but no, I don't think anybody has succeeded. So I'll make some more remarks when I come back next time. I think I'll stop here, and if there are questions, please ask. Babar was asking some questions. Please around, you can ask.
No, I think I got most of it.
Hmm?
No, I got the answers for most of my questions.
Hmm. Okay. Hmm.
But let me just ask, like, so, uh, so this vacuum state. So for this, from the perspective of this operator, it looks like a KMS state if we think of it as some kind of Hamiltonian. So, but this must have some interpretation for in terms of the Unruh effect. So how do you connect it with that, given that the this operator is not bounded below?
This I don't know. I saw a claim which I don't know the correct. No, the Hamiltonian
No, but this is true. I mean, this is true. Like if we don't do this kind of local algebras, if we just do the naive kind of quantum field theory, then one can see that one can define a Hamiltonian for the accelerated observer, and then the vacuum of that observer and the vacuum of the actual quantum field, they are related by the Bogoliubov transformation, and one can see that the transformation gives you a thermal state. So one to the other looks like thermal.
Yeah. So the issue is whether the Hamiltonian confines there. I would imagine that it is the same as the boost operator. This is my remembrance from papers of Segal and Thorne, old papers. So check. Then it will not be bounded below. They may have put a cutoff. Or only will get costly as the case of the boost operator. But the boost operator does not have a boundary. No, that's for sure. So I do not recently, I have checked it.
Mhm.
So what do you do? The Rinder wedge has horizons. There's a light surface bounding it, right?
Yeah.
So imagine a translation of the wedge nose along one of the light direction. So slide the whole wedge within the cone with one side going up, okay? And you get another wedge. So the nose of the wedge would have moved up, but the sides, the horizons would have started at a later point because they were sliding it up. Okay. If you do that, there's a new signal wedge. So first was W1, second is W2, and W2 is contained in W1. So the corresponding quantum and algebras actually also included in one another because of this old requirement of isotope on mirror. And they have their own private Together operation and their own private boost operation. I have heard somebody telling me that the difference between the two boosts there is bounded below. And people, one can do calculations with that, but I have no idea whether it's correct or not. I'd like to raise the literature. I don't know why it should be bounded below, but that's a claim. But the inclusion I told you is correct. It's called the half-sided model. Again, the ideas are very simple. You're just taking the wedge and moving it on a side. Moving the horizon up a side. And trying to see what happens. So, it may be worth investigating that. So, address your question. I think that standard quantum theory will try the only isometry for a linear wedge, say constantly accelerating particle, is boost. And for sure, boost is not bounded below or bounded above in quantum concrete. Cannot be. So, because you can make Lorentz transformation and make spectrum go all over the place. So there must be something else going on here. I don't know. Okay.
Okay.